This is often written as where increment equals 2 is the Laplace operator and is a scalar function. Laplace's equation and Poisson's equation are the simplest examples of elliptic partial differential equations. The general theory of solutions to Laplace's equation is known as potential theory. The solutions of Laplace's equation are the harmonic functions, which are important in many fields of science, notably the fields of electromagnetism, astronomy, and fluid dynamics, because they can be used to accurately describe the behavior of electric, gravitational, and fluid potentials. In the study of heat conduction, the Laplace equation is the steady-state heat equation. Definition: in 3 dimensions, the problem is to find twice differentiable real-valued functions f of real variables x, y, and z, such that in Cartesian coordinates, in cylindrical coordinates, in spherical coordinates, in curvilinear coordinates, or this is often written as or, especially in more general contexts, where increment equals 2 is the Laplace operator or Laplacian, where is the divergence operator which maps vectors to scalars, and is the gradient operator which maps scalars to vectors of f to a scalar, if the right-hand side is specified as a given function, h, i.e., if the whole equation is written as, then it is called Poisson's equation. The Laplace equation is also a special case of the Helmholtz equation. Note: the delta symbol, delta, is also commonly used to represent a change in some quantity, e.g., increment qq plus delta or increment qq plus epsilon q for some very small scalars delta or epsilon. It's used to represent the Laplacian should not be confused with this use. Boundary conditions. The Dirichlet problem for Laplace's equation consists of finding a solution phi on some domain D such that phi on the boundary of D is equal to some given function. Since the Laplace operator appears in the heat equation, one physical interpretation of this problem is as follows. Fix the temperature on the boundary of the domain according to the given specification of the boundary condition. Allow heat to flow until a stationary state is reached in which the temperature at each point on the domain doesn't change anymore. The temperature distribution in the interior will then be given by the solution to the corresponding Dirichlet problem. The Neumann boundary conditions for Laplace's equation specify not the function phi itself on the boundary of D, but its normal derivative. Physically, this corresponds to the construction of a potential for a vector field whose effect is known at the boundary of D alone. Solutions of Laplace's equation are called harmonic functions. They are all analytic within the domain where the equation is satisfied. If any two functions are solutions to Laplace's equation, their sum is also a solution. This property, called the principle of superposition, is very useful, e.g., solutions to complex problems can be constructed by summing simple solutions. Laplace equation in 2 dimensions. The Laplace equation in 2 independent variables has the form analytic functions. The real and imaginary parts of a complex analytic function both satisfy the Laplace equation. That is, if z equals x plus iy, and if then the necessary condition that f be analytic is that the Cauchy-Riemann equations be satisfied, where ux is the first partial derivative of u with respect to x. It follows that therefore u satisfies the Laplace equation. A similar calculation shows that v also satisfies the Laplace equation. Conversely, given a harmonic function, it is the real part of an analytic function, f. If a trial form is, then the Cauchy-Riemann equations will be satisfied if we set this relation does not determine psi, but only its increments. The Laplace equation for phi implies that the integrability condition for psi is satisfied, and thus psi may be defined by a line integral. The integrability condition and Stokes' theorem implies that the value of the line integral connecting 2 points is independent of the path. The resulting pair of solutions of the Laplace equation are called conjugate harmonic functions. This construction is only valid locally, or provided that the path does not loop around a singularity. For example, if r and theta are polar coordinates and then a corresponding analytic function is, however, the angle theta is single-valued only in a region that does not enclose the origin. The close connection between the Laplace equation and analytic functions implies that any solution of the Laplace equation has derivatives of all orders, and can be expanded in a power series, at least inside a circle that does not enclose a singularity. This is in sharp contrast to solutions of the wave equation, which generally have less regularity. There is an intimate connection between power series and Fourier series. If we expand a function f in a power series inside a circle of radius r, this means that with suitably defined coefficients whose real and imaginary parts are given by therefore, which is a Fourier series for f, these trigonometric functions can themselves be expanded using multiple angle formulae. Fluid flow. Let the quantities u and v be the horizontal and vertical components of the velocity field of a steady incompressible or rotational flow in 2 dimensions. The condition that the flow be incompressible is that, and the condition that the flow be rotational is that if we define the differential of a function psi by, then the incompressibility condition is the integrability condition for this differential. The resulting function is called the stream function because it is constant along flow lines. The first derivatives of psi are given by, and the rotationality condition implies that psi satisfies the Laplace equation. The harmonic function phi that is conjugate to psi is called the velocity potential. The Cauchy-Riemann equations imply that thus every analytic function corresponds to a steady incompressible, a rotational fluid flow in the plane. The real part is the velocity potential, and the imaginary part is the stream function. Electrostatics. According to Maxwell's equations, an electric field in 2 space dimensions that is independent of time satisfies an, where ρ is the charge density. The first Maxwell equation is the integrability condition for the differential, so the electric potential phi may be constructed to satisfy the second of Maxwell's equations, then implies that which is the Poisson equation. It is important to note that the Laplace equation can be used in 3-dimensional problems in electrostatics and fluid flow just as in 2 dimensions. Laplace equation in 3 dimensions. Fundamental solution. A fundamental solution of Laplace's equation satisfies where the Dirac delta function delta denotes a unit source concentrated at the point. No function has this property. In fact, it is a distribution rather than a function, but it can be thought of as a limit of functions whose integrals over space are unity, and whose support shrinks to a point. It is common to take a different sign convention for this equation than one typically does when defining fundamental solutions. This choice of sign is often convenient to work with because minus delta is a positive operator. The definition of the fundamental solution thus implies that, if the Laplacian of u is integrated over any volume that encloses the source point, then the Laplace equation is unchanged under a rotation of coordinates, and hence we can expect that a fundamental solution may be obtained among solutions that only depend upon the distance r from the source point. If we choose the volume to be a ball of radius O around the source point, then Gauss' divergence theorem implies that it follows that on a sphere of radius r that is centered on the source point, and hence note that, with the opposite sign convention, this is the potential generated by a point particle, for an inverse square law force, arising in the solution of Poisson equation. A similar argument shows that in 2 dimensions where log denotes the natural logarithm. Note that, with the opposite sign convention, this is the potential generated by a point like sinc, which is the solution of the Euler equations in 2-dimensional incompressible flow. Green's function. A Green's function is a fundamental solution that also satisfies a suitable condition on the boundary S of a volume 5. For instance, may satisfy now if U is any solution of the Poisson equation in V, and U assumes the boundary values G on S. Then we may apply Green's identity. which states that the notations Un and Gn denote normal derivatives on S, in view of the conditions satisfied by U and G. This result simplifies to thus the Green's function describes the influence of the data F and G. For the case of the interior of a sphere of radius A, the Green's function may be obtained by means of a reflection. The source point P at distance ρ from the center of the sphere is reflected along its radial line to a point P that is at a distance. Note that if P is inside the sphere, then P will be outside the sphere. The Green's function is then given by where r denotes the distance to the source point P and r denotes the distance to the reflected point P. A consequence of this expression for the Green's function is the Poisson integral formula. Let ρ, θ, and φ be spherical coordinates for the source point P. Here θ denotes the angle with the vertical axis, which is contrary to the usual American mathematical notation, but agrees with standard European and physical practice. Then the solution of the Laplace equation inside the sphere is given by where a simple consequence of this formula is that if U is a harmonic function, then the value of U at the center of the sphere is the mean value of its values on the sphere. This mean value property immediately implies that a non-constant harmonic function cannot assume its maximum value at an interior point. Electrostatics in free space. The Laplace equation of any electrostatic potential must equal 0 since ρ is 0 in free space. Taking the gradient of the electric potential we get the electrostatic field. Taking the divergence of the electrostatic field, we obtain Poisson's equation that relates charge density and electric potential. In the particular case of the empty space, Poisson's equation reduces to Laplace's equation for the electric potential. Using a uniqueness theorem and showing that a potential satisfies Laplace's equation and the potential has the correct values at the boundaries, the potential is then uniquely defined. A potential that doesn't satisfy Laplace's equation together with the boundary condition is an invalid electrostatic potential.